are you laughing about now? Okay, so yeah, acid-promoted reaction. HI is the best because the iodine's the largest. Fluorine's the smallest, right? But HF is also a weak acid, so it doesn't promote the reaction as well because part of the promoting or the speeding up of the reaction is to protonate the oxygen, and it just doesn't do a good job of that. So that's the basic trend. So this is the problem that I left off on. We're doing an acid-promoted reaction. And the products for that, one was this. And the other was, remember, this is a nucleophilic reaction, right? So I'm going to protonate this oxygen. I'm going to attack it on the first one and kick the alcohol off. So the first intermediate product, like after the first HBr, is actually going to be this. And then a second equivalent or second mole, if you want to think about it that way, of HBr will come in. And then I'll get this. And the reason for the inversion here is because it's an SN2 reaction. This one's also SN2, but there's no stereochemistry at that point there, so it doesn't matter. Okay.
For that OH, you don't need to use any potassium chloride, pyridine, or anything?
For the OH, yeah, the solvent. What is the solvent for this? Probably just methylene chloride. Yeah. If you can't use pyridine because the HBr will protonate the pyridine.
So you get all three products?
Yeah. Oh no. So what you end up with as your final products are these two. But you have to remember that in this acid-promoted reaction, the first product you get is this. It's the alcohol. In this case, that has the same configuration. At some point, because it's an SN2 reaction, when you make the alkyl halide, there's an inversion in the process. Okay.
So if you have HBr to the reaction, can you stop it?
I think it'll end up being mixed. So the answer is I don't know what the mixture's like. If you just have one, yeah. Didn't talk about this in chapter 11. I knew this was going to come up later. This has to do with the oxidation of peroxides. I just want to show you the initial part of the mechanism and then show you how the product forms. And we're not going to spend a lot of time on it, but we see this kind of reaction a lot in organic fatty acids. Organic fatty acids are what you find in like fatty acid cell walls, or if you buy oils, like unsaturated oils, you see that kind of thing a lot. Hey, Nathan, I have a question for you. When you have a question, Nathaniel, when you have a question, your arm's always going to... By the way, Nathaniel got in a horrible accident, so he has to have his arm elevated all the time. We need to come up with a way for you to signal me, like wave with your right hand like this, because I look over and I see your hand. You need to leave it up. I was like, you don't have a question, do you?
I had a question.
Okay, good. I wasn't sure. He's always got his hand up because he has to have his hand up, and I'm like, oh, I don't know.
So on the previous one, isn't it protic? So why SN2 is protic?
Back here, that's aprotic.
Okay, isn't it under acidic condition?
Yeah, but like HBr, and oh, I see what you're saying. But the primary solvent is methylene chloride, and you're adding a little bit of HBr. So I don't think you would consider that, like the solvent's not protic.
Okay.
Yeah. Sometimes we do these reactions with the alcohols. We call them solvolysis reactions, and we consider that protic because the solvent is also the reagent, and it's primarily protic. Right? like solvolysis reactions with alcohols or water. Okay, so in this reaction, the first step in the mechanism is this. That is, you have some sort of initiator. Now, the initiator can just be caused by light. And you can take oxygen that's double bonded, hit it with the photon. That's the squiggly photon sign, right? You know, the waves that go like this. And then what happens is one electron goes like that, and one electron goes like that. And it looks like a guy with a cigar who's not happy. Took you a second. And it ends up looking like that. So that actually can be the initial radical that forms. So just leaving like oil out, like unsaturated oils out in light can promote this reaction, okay? So once you have that radical, it turns out the hydrogen next to the oxygen is more reactive. And the reason that it's more reactive is because this has resonance. So it can form this radical that looks like this. Trying to get my dots to form. So you can end up having something that looks like that. Is that right?
On the right. On the carbons.
I'll double check that. It doesn't seem right to me. 1, 2, 3. I think I have too many electrons on there still. But anyways, because of the oxygen that is next to it, that stabilizes that radical, and as a result, they form fairly easily. In fatty acids, in particular, you have a lot of structures that look like this. And these are very reactive because of the pi bond that's next to it. So once you form this radical, you can form the radical here. It attacks an oxygen, so this comes from oxygen again. And you form this known as a radical these peroxy ether radicals. And then this protonates by attacking another ether, and so you end up with this guy here.
Okay. The one that your question, one of the workers jumped to the carbon to light, because now that oxygen.
No, I think I'm remembering something wrong, so I'm going to go look at this.
That's not.
Yeah, I don't think this is going to stabilize now. That was my, when I was looking at it, I was thinking about like alkenes and how they oxidize easily. So I'll have to look at that. And I think that's not a reasonable reason why it happens. It's probably more an inductive effect now that I'm thinking about it. But my first thought was that's the mechanism, so you can maybe leave that off. But the end result still is the same. You form a radical, you pull the hydrogen off of the carbon next to the oxygen, and then you have these propagation steps, which give you these what are known as peroxy ethers. And it turns out those things are really dangerous. You guys were using diethyl ether. This is diethyl ether if you don't recognize it. It was diethyl ether that we used in the lab the other day. One of the stipulations on diethyl ether is you're usually not supposed to use it for more than a couple of years, because if you think about, and these kinds of accidents used to happen a lot more when people had glass bottles. You'd have a glass bottle, and you know how you have those glass stoppers that go into them? And then oxygen can get in from here, and ether is coming up to meet it, like here, and they would form in this gap between the two pieces of glass, and they're explosive when they decompose. So when you grab the bottle and you went to twist it, it would blow up. So they told people, hey, you can't do that anymore. So most of the bottles we have for ethers are plastic lined, and you buy what you use for a year, and then you get rid of it. And then we also have peroxide test strips for all our ethers. So like every time you get a bottle of ether, you date when you got it and when you opened it, and then you test it like once every like 3 to 6 months or so.
Actually, I have a question. I thought the point of doing, the fog against the glass, I thought that was to prevent oxygen from getting in. That's why, like, on
Right, but you still get some, like, no, it's not a perfect world, so you still get some oxygen coming in. You still get some ether coming up.
Okay.
Yeah, and apparently it crystallized. I've never seen it, although we did have a big bottle one time. Back about 15 years ago, we were cleaning up a lot of chemical waste. And in this big bottle were all these crystals on the inside. And we're like, what's that? And everybody's like, it's all completely unlabeled. We're like, we don't know. So they brought the bomb squad in, and they brought the robot that moved it in. It's very exciting. No. I think what they do with those things is they blow them up and they worry about it later. Yeah.
You didn't do an IR?
All right. The termination, the termination step, by the way, for the reaction looks something like this. It's a coupling reaction. Again, pretty straightforward kind of radical reaction stuff. Okay, so, oh gosh, I hate this section. I hate this section. Let me skip this slide and I'll come back to it, okay? I'm going to start with this slide. Epoxides, you can name them 2 different ways. So you're going to learn both. An epoxide is a 3-membered ring with an oxygen as part of the 3-membered ring. So you can name it as an oxyrane, and the oxyrane is the 3-membered ring. So this is the parent. And it's pretty common to see this nomenclature. There's actually a 3rd way, but we're not going to go to the 3rd way. And in terms of numbering, the number 1 atom is the oxygen. Okay? Always. Yeah. We're going to use both. We're going to use both.
What are we doing right now?
We're doing this one right now. I'll talk about this one up here in a second, and you can see how they compare. So then what you do is, if the ring is the parent, then everything else off of it's a substituent. So you just name the substituents on the parent ring.
Most of the ones that have oxygen as the parent, like, functional group, usually first. Like with the alcohol.
Yeah, but the alcohol's the carbons first, yeah. But it's not the oxygen that's first, it's the carbon on the oxygen. So in the ring, the oxygen is first. So this is known as oxyrane, and this nomenclature actually, there's a lot of nomenclature that comes off of this. To name this one, then this is, right, methyl and methyl. This is ethyl and ethyl. So when you're going around the numbering, E comes before M, so the numbering becomes alphabetical in this case. So 1, and this is 2,2-diethyl, 3,3-dimethyl oxyrane. Pretty straightforward. It's a handy nomenclature system to know because, let me just go back up to that slide now. Oxane, oxetane, oxalane, these are the names for the ring systems that have 1 oxygen in them. I think, if I'm not mistaken, they're based on oxane. Where you may have seen oxanes before is you're typically seeing them as environmental hazards, actually. And there's oxanes, part of the group of oxanes are these. This is 1,4-dioxane. Ran out of space. You can imagine it ends like this down here, but I ran out of space down there. So dioxin is, you may know what dioxin is?
Are we going to see bicyclic compounds for these?
No.
Okay, cool.
Yeah. Good question. Because guys, have you guys ever heard of like dioxins? What have you heard dioxins in the context of? What's that? No. It's a carcinogen though, and they've done a lot of studies on it. I'm not sure where the research stands now. Originally, when they tested these in mice, these are the most cancer-causing agents that we know of.
And what's it in? Like everything.
It was like, I think it was a contaminant in pesticides. So they're being sprayed all over the place as a contaminant in pesticides. But then what happened in the research is somebody showed that they're a lot more cancer-causing in rats than they are in humans. So, the joke went then, this is the most cancer-causing agent in the world for mice or rats, right? Not for humans, but it is something you worry about. But they have a different metabolism. But there was a whole big stink about it for many, many years. So dioxins are an important class of compounds to know. But the numbering system's the same. So this is the number 1 atom in each one of these. Okay, we're only worrying about oxirane and not the other ones for now. Okay, but I just wanted you to know that there's a whole other nomenclature system. And dioxins you see a lot.
And you go you number the side with the most substituents first?
Well, you number the side, like oxygen's always 1, and then you go down the side that gives the first substituent the lowest number.
Oh, okay.
And if it's a tie, it's alphabetical. So it's the same as any other nomenclature rule. Right. First substituent, lowest number, or if it's a tie, you go alphabetical. So the other thing about the other nomenclature system, for epoxides is using the epoxy nomenclature. So you can say, for example, if this is the longest, and we don't do this for anything else, but here's the longest carbon chain, and then what they say, this is 2,3 epoxy, because it's the epoxide between the 2 and the 3 carbon. So then what happens is everything, right, these are the same compounds, right? Everything attached here becomes substituent. So now this is 2-methyl, 3-ethyl. It's not alphabetical anymore in terms of the numbering because the lowest numbered substituent is the methyl group in this case. Okay, questions?
We only use epoxy to have the
Oh, epoxy is always 3-membered ring, so it's always 2 adjacent carbons, so that's how you do that, yeah. So let's see, what do we got here? Let's try naming this.
So when I said bicyclic compounds,
What's that? Oh, well, yeah, but here. So let's call this 1, 2, 3. This is ethoxy. Yeah, we're not doing the bicyclo nomenclature with an oxygen in it. Right? So this is, the parent is what? It's 1, 2, epoxy, and then cyclohexane.
So do we switch over to the other method?
Oh, so we have to do the 1, 2 because there's no way to do, think about in terms of the nomenclature. Sorry. Like on this side, when you use oxirane nomenclature, these substituents can't be connected. Since it's connected, you have to switch to the top one. Yeah? So you have to know both. So that's 1, 2 epoxy cyclohexane, and then it's 3 ethoxy, so they'll go. And then you have to designate stereochemistry. So there's 3 stereo centers on that one. let's see. This is 1, 2, and 3, and there's a hydrogen going back like this, right? So this is going like this. That's S. And then this one is 1, 2, oops, sorry. Make sure that's oxygen. Yeah, that's 2. I'm pretty sure that's 2 and 3. So it's going like this. So that's actually, let me double check that one. That one's tricky. Let me erase some stuff on here. So I'm gonna try to do this one correctly here. This is 1 for sure. There we go. 1. Okay. And then let's see. There's a carbon here. It's attached to a carbon with an oxygen bonded to a carbon. That's this guy. This is a carbon, right? This is the one we're trying to designate the priorities to. This has got to be 1 because it's oxygen. This is a carbon bonded to an oxygen, right? Here, this one is a carbon bonded to an oxygen bonded to a carbon. So they're the same at that point. So if I'm here, if I'm going this way though, watch. 1, carbon bonded to oxygen bonded to carbon. Then this carbon is bonded to a carbon. And this carbon is bonded to a carbon. This carbon's bonded to, sorry, this carbon's bonded to a carbon. But if you go here, I don't know if you're keeping track of all this. Carbon bonded to a carbon to an oxygen, then you go back to here. To a, yeah, you just have to keep going till it. So that breaks the tie. So I'm pretty sure this is 2.
How do you know which route to go though? Following left, following right?
So no, you go in all directions. So that's what makes this one really hard. I never thought about why. I think when I looked at the answer for this, they didn't designate that as a stereocenter. I decided, well, I better designate that, otherwise you can't tell which if it's going up or down. So for this carbon that's here, right? It's connected to this carbon, which has, and if you think about this carbon is on an oxygen. I'm going to do it like this, and a carbon. And this carbon is on an oxygen and a carbon. So then you have to do each one of these separately. So this carbon's on a carbon and 2 hydrogens. The highest priority, though, that it's attached to is this carbon that's actually down here. When you go to this one and you go this way, going this way, on this oxygen, it's bonded to a carbon.
Even if it's itself?
Yeah. So you just keep going. You have to be able to designate a priority, and the rule is you just keep going till you break the tie. So that oxygen is bonded to a carbon that's bonded to a carbon, bonded to an oxygen and a carbon. So the tiebreaker is going to be this oxygen here. Because when you go the other way, if you go down to here, right, it's going to run into the carbon bonded to the oxygen's bonded to a carbon, and that one's bonded to a carbon. I'm not counting the hydrogens because they're lower in priority. So I'm just looking at the highest priority attachment. And then this carbon is bonded, that's this, to this carbon. So we're actually, this carbon here, that one there, is the same as this carbon here. So you're actually crossing in the circle and going around. But the deal is in this top branch, all right, carbon, this is a carbon with an oxygen, carbon, carbon, oxygen, and this one is a carbon, oxygen. It never repeats back to the oxygen. So the tiebreaker should be the oxygen that is in the ring that you counted the first time. So this is 2, which makes this 3. So this is going like this. So that's R. So that was R and S. So it's 1 S, 2 R. Sorry, I didn't mean to do that. I actually didn't mean to do that to you guys. I thought it would be an easy tiebreaker. I didn't think about it having to go back through the ring, but oh well. Hopefully you followed some of that. And then, and this guy we have to do, oh my God, this one's easy. That's 1 and that's 2. So this is 1 and that's 2. So it's going like that. So it looks R, but it's actually S, so it's 3S. And that just goes in front of everything. And that's the horrible mess of nomenclature. This one, because the substituents aren't simple, probably easiest, again, to go 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. But rather than do that, I'll put the name up for you and go through it the whole time again.
I have a question about the R acid stuff. Is there ever a chance for epoxide to have like a DAS and a wedge on the same oxygen?
Oh, no. Because it's a 3-membered ring, you can't have one above the ring and one below the ring.
So then isn't it kind of pointless to go R and S? If you just know if one is S, then you know the other one must be the same direction, be wedge?
It depends on what the substituents on either side are, probably. I have never really thought about that hard. Because you might not have a hydrogen here. You might have something else here. You might have a nitrogen, or you might have another carbon attached instead of a hydrogen. That might affect it. Yeah.
We have 3 ethoxy before 1, 2 epoxy. For the nomenclature, how we go in alphabetical order?
Yeah, I might
Talk
have.
about priority for one to be in front of the other.
No, I may have had to do that the other way, actually.
Because there's E and E and T.
Yeah, but
Yeah.
isn't 1, 2 epoxy cyclohexane, isn't that for like the parent? Or the cyclohexane?
No. So the parent is the cyclohexane, yeah. So looking back on it now, right, I should have probably switched those numbers, yeah.
1, 2,
Yeah.
3.
So I'll fix these and I'll post them. I know it'll be a question, so it's coming. Yeah. So I'll fix it, and I'll double check whether or not you have to do the ring, but I think you have to do the epoxy ring. Okay, so how do you make epoxides? Epoxide, we talked about this before. Peroxyacetic acid, MCPBA, forms the epoxide ring. I'm not going to spend a lot of time on that mechanism, but that's an easy way to form them. One of the things to know about epoxides is the stereochemistry of the groups, if they're cis in the product, are still on the same side. Okay, they're still cis on on the same side of the ring. If they're trans on the ring, then one will be front. Or sorry, trans in the double bond. Then on the ring, one will be forward and one will be back. Okay. So when you form the epoxide, depending on what the stereochemistry of the reactant is, you only get one stereochemistry on the product. Hang on. Yeah, for something that's cis and for something that's trans. Make sense? Yeah, so the oxygen is essentially syn addition, both to the same carbon. Okay. The other way that you can make epoxides is through halohydrin formation. And if you remember what halohydrin formation is, simple alkene, Br2 and water, and that forms the halohydrin. This is an anti-addition. So what happens in the mechanism, because the OH is at the bottom side, opposite the Br2, and if you deprotonate this oxygen, because they're right next to each other, it's very susceptible to nucleophilic attack once it's deprotonated. Okay? So you can form an epoxide in the halohydrogen formation. The only catch in this is when you form this, right, the O can be at the top and the Br at the bottom, or the Br at the top and the O at the bottom. So if there's stereochemistry, and this one isn't because it's meso, but if there's stereochemistry, you form a pair of enantiomers all the time. Okay. So this is the mechanism, right? Halohydrogen is formed, use OH to deprotonate. The oxygen attacks nucleophilically to the BR leaves. They're showing you that it has to happen like elimination reactions. If you remember, elimination reactions have to be anti-periplanar, where one group is up and one group is directly down, so have to be in the axial position. And so if it's in the axial position, then the oxygen can attack and displace the bromine, and then you end up with your epoxide that forms. One of the questions, I think, in the homework that I assigned talks about rates of reactions. If you have a large group, so let me draw on this slide really quick. This reaction will be faster if you put a large group so that it forces those two to be in the axial position. And the reason that is because the large group wants to maintain the axial position, and it holds the oxygen and bromine in their axial position so that it can attack as a nucleophile in that anti-periplanar fashion. Yeah, large groups in equatorial position, and then to force these two to be in the axial position. On the other hand, if you substitute that and you put it like this, you notice I put that now in the axial position. It's going to force it to the equatorial position, so then these will get forced to the equatorial position, and the reaction rate's much, much slower, simply because the oxygen can't backside attack on the bromine.
Why does those variable terms go to the backside instead of just making it? Oh, never mind.
Yeah, SN2.
There you go.
Yeah.
Sorry.
Okay. So in essence, if the two groups are together on the alkene and they're in a ring, then you'll end up with this same kind of configuration. They have to be, because the the halohydrogen has to be anti, the R groups will have to be lined up in the same configuration. So halohydrogen and MCPBA, the peroxyacetic acids, produce the same stereochemistry. Although one has an intermediate and one doesn't. Okay, so for asymmetric, going either route, they say racemic mixture, so they're tipping you off to the answer. One looks like this. Sorry, I'm going to erase that double bond in a second. Actually, I can erase it now. I'll just say this. ME. Okay, so all I did is I redrew it, right? And then the epoxide is going to form here, like this. And if it does that, that group's going forward and that group's going forward. And the methyl and the ethyl are in the back, pointed away. Now, it says a racemic mixture because the oxygen doesn't have to just add from this side. It can also add from the bottom. And when you add it from the bottom, you're going to still have, let me do it like this again. I'm just going to redraw the original structure. oxygen can be down like this as well, that group will still be in the forward direction, that'll still be in the back. Like that. Now if you take this molecule and you flip it over, right, or if you look at the plane like this, those are mirror images of each other. Okay. So because the oxygen can either come from the top side and the bottom side, you end up with a racemic mixture on asymmetric alkenes. Okay, so this happens. There's a picture of it. It's a little bit better. If you think of the molecule in a plane like this, then what ends up happening is the oxygen can be from the top or the bottom. And then just drawing the plane of symmetry across here, you can kind of see how that's mirror images top and bottom. Okay, so those are enantiomers of each other. Turns out that's always the way it is. You get a racemic mixture. So one of the big advances in synthetic chemistry was the ability to not form both, but just form one. Okay? So when you form one, the way it's done is known as Sharpless epoxidation reaction. Now the Sharpless reaction requires that in the allylic position to the double bond, you have an OH group. And here's the thing. If you want to favor epoxidation on one side versus the other side, then the thing that does the epoxidation has to be asymmetric as well. You have to have a chiral reagent to produce a chiral result. So if you think about, like, I don't know how to make sense, if this is the alkene, like on the, I'm going to use George's bag because it's so big. That's the alkene. If I was the chiral reagent, if this has an OH group that attaches over here, right, and the epoxide comes in from the top like this, because it's also attached to this center. So there's an epoxidation reagent that goes like this. This alcohol binds to my side like this, right? Has to have a certain geometry here because I have a shape like this. And when the epoxide comes in, and this is the peroxide comes in, it forms the ring on the top side of the double bond because I can't reach around the bottom side because the peroxidation mechanism is from here. But that is only true, and the reason it works is because on the double bond, right, on the allylic position, you have that oxygen that will bond into my side. Now, the reagent, does that make sense? Kind of? Like, if I was like, if you put the double bond, if you put the reagent like this and the oxygen was over here, right? So now I'm the mirror image of myself, what I was before, right? But this thing has to flip over, I will epoxidize from the other side. So the idea is, in order to form a chiral result or an asymmetric result, you have to have an asymmetric reagent. And so what Sharpless did is he took this complex ion, from Chem 1B, transition metal stuff. This actually forms an octahedron. And then what he does is, there's actually two of them that come together. It forces the peroxide to, hang on. How am I going backwards? I thought there was more to that. Oh, sorry. Yeah. It forces the peroxide to come from either the peroxide to be formed either from the top or for the epoxide to be formed either from the top or from the bottom. So the mnemonic that you need to remember, okay, because I'm going to ask you one of these because it's such a common thing to see, is that if you put the oxygen of the allylic alkene on the top right, the reagent that they use is this plus diethyl tartrate. It's actually a biological compound, tartaric acid, but it has ethyl groups on it. Causes to the epoxide to form at the top of the double bond. And in terms of like enantiomeric purity. Like when we say racemic, it's 50-50. In terms of enantiomeric purity, it's more like 99-1. So having chirality in the catalyst, and the catalyst is this molecule plus this diethyl tartrate, that's this guy here. You notice these are mirror images of each other. Forces asymmetry into the product, into this. Okay. So if it's the minus reagent, again, if you put the oxygen on the right side, top right hand side, the ring forms at the bottom.
Okay, aren't those exactly the same structure except that one's sitting on the side?
No. So the way this is supposed to be viewed is like this is the plane. That one was oxygen at the top above the plane. And this one is oxygen at the bottom below the plane. So if it looks like it's the same, you think about it like this. You drew a line through here, right? Mirror image from here to here, here to here, here to here, here to here. And there is no plane of symmetry in the molecule. So they're mirror images of each other.
Or if you have that bottom molecule.
Yeah, if you grab this molecule like this, here's R3 and R2, and I grab it, right, this is R2.
Yeah.
I flip it over to do that. R2 is now over R3. So they're not the same, yeah. Any other questions? That's a lot. I thought about showing you the complex, but it involves two titaniums bonded to each other. I decided, just remember the mnemonic. It'll be easier. Okay, so really the last thing I want to cover in this chapter is the ring opening of epoxides. One of the reasons that we're in... So the idea is, and we covered this in, I don't know, chapter long time ago, 9 or 10, right? Bring in a base, it attacks this carbon, this breaks, you form an oxygen oxide ion here, and you have the alcohol functional group down here. This protonates and forms a diol. So this was the mechanism for the formation of diols from epoxides. Overall, it was an anti-addition. Yeah. Okay, so let me skip all of that. The reason for how fast the reaction is, ethers are very stable to sodium hydroxide. Epoxides are very unstable to sodium hydroxide. They essentially have the same transition state, a breaking of a bond, but this molecule, the epoxides, start at much higher energy. So the ring strain, we talked about this in lab last semester, the ring strain causes the starting material energy to be higher, so that means that activation energy is going to be lower. So again, activation energy is this, right? And so that since that's lower, they're much more reactive. So the things you can do with epoxides, you can actually produce ether alcohol functional groups, and then you could oxidize that and make an aldehyde, for example. So you could add 2 carbons and then put a functional group at the end. So you can bring alkoxide ions in as nucleophiles. Cyanide will work as a nucleophile. Sulfides are very good nucleophiles because of their size, right? And they're not strong. They're not strongly basic, so they make very good nucleophiles. You can also use Grignard reagents, and you can use lithium aluminum hydride. So if you use lithium aluminum hydride on it, then when you open the epoxide, you just end up with the alcohol functional group. Okay. So lots of different things that you can do with this. Now, if you remember, on substituted epoxides, when the nucleophile attacks, so the nucleophile is going to come in and attack. It has choices. It could go here, or it could go there. Which side does it prefer to attack? What's that? Yeah, the less the one with the fewer substituents on it. It's this one. You can make the argument, and it makes perfectly good sense, and it's mostly true, is there's less steric hindrance. It's a nucleophilic attack. The less sterically hindered side gets attacked. It turns out, though, that's not entirely true because this is a 60-degree angle over here. This is almost planar. There's very little steric hindrance to that. So there's two things. If the regio chemistry of this molecule follows one, right, SN2 less attacks the less hindered side. And the second thing is the transition state has a negative charge in it. The negative charge will show up here, and it's the less substituted side. If you remember carbanions, like being on less substituted carbons, because there's a less electron donation at that point. So as a result, in both these instances, the nucleophile attacks the less sterically hindered side, and this one it'll attack here. So your product for the bottom will be like this, and then the nucleophile will be like this. All right. This implies that the nucleophile came from the backside of this oxygen on the less substituted carbon. For this one, right, it's going to come on this side, so you'll end up with, and this is not a chiral molecule, so it doesn't really matter, but you'll end up with this, and then your nucleophile will be on the underside of it. Okay? But they come in from opposite sides, so the products will be on opposite sides, or the functional groups will be on opposite sides. Turns out, we talked about this last semester, in acid-catalyzed epoxide openings, it's the opposite. It actually attacks the more substituted side. Okay? And in epoxide openings that are, I'm going to skip these, hang on, like this, right, the major product is, let's see, where are we at? Is actually like this. Oops. So when the nucleophile attacks, if you're using like HCl or HBr, right, you'll end up protonating the oxygen. Ignore the top pathway. This is the one that doesn't happen. You don't attack the less substituted side, even though it's less sterically hindered, right? You end up attacking the more substituted side down here and adding the halide at the more substituted carbon. Okay. Hang on. So let's go over the mechanism real quick. Talk about how it's different. So your product's going to be that. So that's the main reaction. The mechanism is this. And then you end up with and what's missing there? Positive charge here. Okay. Now, this is still a nucleophilic attack that causes the bond to break. Here's my nucleophile. could either come in here or it could come in here. The end result is that, because I've just shown you the main reaction, is that it attacks at this point here. So even though this side's more sterically strained because it has an extra alkyl group on it, it turns out to be more reactive because this bond is actually a little bit weaker than this bond is. The reason for the weakness of the bond is if you think about as this bond breaks and you start pulling the electrons towards the oxygen, like in that direction, you're going to end up with a transition state that looks like this. So in this transition state, as this bond breaks and the oxygen pulls the electrons away, it ends up forming a positive charge on the carbon as it breaks away. Now, it could happen on either side, right? It could break on this side or on this side. But when it breaks on this side, because this carbon has more substituents on it, that positive charge is more stabilized. So we have these two pathways. Here's the reactant. And let's say here's the intermediate, or in this case, I could just do product. One pathway might be this one. And then, hang on, let me do this. That's on a different enough color. That's when this bond breaks, let's say. But this transition state is stabilized by substituents. On the other side, that's this side, it's going to be higher in energy. So even though the reactant is the same and the products are about the same energy because they're both alcohols, right, with a substituent on them, the transition state energy is going to be higher for this side because there's no stabilization for this top line. Okay, so as a result, this pathway is faster going through this carbon. And so you end up getting the nucleophile on the more substituted carbon. Kind of like you'd expect for like a Markovnikov's rule, right? Because the nucleophile ends up on the more substituted carbon for that. So if this is the reagent that we're using and we have an alcohol here, okay, and we protonate it, right, the oxygen's going to protonate, that causes this to attack at the more substituted side. So you end up having the oxygen coming from the back side over here. That gives us the stereochemistry where the methyl group has been pushed forward and the alkoxide part is from the backhand side. Okay. Well, actually, that's all I really wanted to cover for this chapter. There's some stuff on synthesis at the end. I don't want to go over the thiols and sulfides in this chapter because it's just a whole nother thing that of marginal importance right now. Yeah, in terms of studying, skip this section. All right. But the next section, this is a long section. Synthetic strategies of epoxide you should go over, okay? But again, it's just synthesis, more synthesis problems. So one of the things that they talk about in the synthesis strategy, just sort of summarize some of this. If you use epoxides in synthesis problems, one of the nice things about it is it always introduces a 2-carbon link here. So a good way to add 2 carbons is by adding epoxides with a nucleophile. Okay, use a nucleophile, add the epoxide. Epoxides can be anything, open with anything like Grignard reagent, acetylide ions, nitriles, CN minuses like can be added, cyanide can be added, sulfites can be added. There's a lot of different things that you could add to that. So I'll let you guys look at those sections, but yeah, skip 1411 and then do 1412, and 1412 is the last section. So.